talking about was what we call garbage collection is just really automatic memory management. So you have to manage memory somehow. You can do it manually, or you can let the computer do it. There was a great question last time, actually after class, about could you do something where you allow the user to try to do some manual? And there are some things like that that will give some hooks or other ways of a user to explicitly say, yeah, you may not be able to tell, but I'm not actually using this. By the way, one thing that you can do in Java, if you're not already aware, if you're done with something, since Java will do automatic garbage collection, assign that pointer to null. Right? Now there's nothing referencing the previous memory. So if you ever want to, it's just a useful thing in Java. So we talked last time about the goals of this. Soundness is never reclaim memory that's still in use. This is the cardinal rule. The other goals, though, are utility, which is collect as much as possible otherwise. Okay. And we talked about how these two are actually in conflict in the sense that I can determine, so there might be, first off, it's totally possible to achieve perfect soundness, right? Never throw away anything. But the issue is you'd like to still throw away as much as possible that they're not going to use. We talked last time about how deciding whether they're going to use that in the future is undecidable. It's in the same category as the halting problem. And so if we can't tell for certain that they're never going to use it, it might be true that they might never use it, but we might not be able to actually determine that computationally. And so what we really have to do is think of it as don't throw away anything that they might possibly still use. If I can determine for absolute certainty that they can't use it, then I'll go ahead and throw it away. But otherwise, we have to err in favor of soundness over utility. And that means for every garbage collection system out there, there is potentially stuff that the garbage collection system could throw away, but it will not because it can't be absolutely certain you're not going to use it in the future. And then the final point is efficiency. It just simply means don't add a lot of overhead to the runtime system. Right? If the language is going to be going through and doing garbage collection, you don't want that to slow the system down. So, I mentioned this before, again on this point of there's this idea of there are things that might be true that we can't prove are true. Shows up throughout computer science and actually throughout mathematics as well. Also in the scriptures. So, getting back to where we, I think, left off last time. Most garbage collectors will typically work in the following fashion. One, identify what space could be reclaimed, and then go through and reclaim it. Okay. Now, one of the things that's really important with this is to understand that memory is just memory. It's RAM. You put bits in, you get bits out. There's no separate store that says this memory is in use, this memory is free. It's totally up to you to be able to keep track of what that is, or within the programming language, it will try to store information about what is in use and what is free. But the place it has to store that is in memory. Does that make sense? So there's no separate place to keep track of what memory is in use or not. You have to actually use that in the memory. You can't put a particular bit pattern and say, oh, this bit pattern means this is free, because that could be a perfectly valid bit representation of some value in some data type. So what you need to do, or the typical structure, is that your heap is going to be organized into blocks of memory. In other words, you organize it. The RAM doesn't know any different. You'll organize it into blocks of memory. Blocks can store data that the program's using, or they could be free blocks of memory that are available to be allocated later. You have to actually keep that information in the memory itself. And so one of the things that's important to keep in mind is that the typical implementation is that every time you allocate something on the heap, it's not only allocating the amount of space you're allocating, but there's a header as well. And that header can be small or it can be big. Older Unix kind of systems, it was only about 12 bytes. Java, last I looked, it was about 40 bytes, and it might even be more these days. Now think about that. You might think, I'm only allocating 4 bytes. No, you're not. You're taking 44 bytes out of the memory, okay, because of the overhead. So keep that in mind with some of these things. But it also means those headers store information that say how big the block is that's allocated memory, how what data type it is potentially, if the Java runtime system will do that. Maybe all kinds of other information that's kept with with that data. So typically you're going to have something where you're going to have, so if this is your heap, what you might have is a common arrangement, and the different languages will do this differently, is that the pointer that that's actually stored with the data might actually point to sort of the data, and right before that in memory is the header. Now that's how most C systems do it. I'm not sure in Java. So if you think about it from C standpoint, that pointer really is pointing to the data. However, the memory management system, now this is not automatic, but you remember you still have new, delete, or malloc and free if you're old school. You can, if you actually look at negative offsets from that header, or from that pointer, you'll actually see header information that stores, again, information like how big is the block of allocated memory. So in this header is going to be something that actually indicates how big that block is and where the next memory would start after that particular block. You see the idea? Now the other thing is, if there's free memory, if you have some block of free memory, you'll also have a header there. And this header would include things like, here is a block of free memory, and here's how much free memory there is. And then, by the way, one of the things we'll see is that many memory management systems will leave memory fragmented, which means you don't always have one big free block to just keep whittling away at. You may have chunks of free blocks. And so you'll see things like this, where part of the header for a free block is actually a link to the next free block and the next free block. So in other words, you're keeping a linked list to track where all the free blocks are. The problem is you have no other memory to store that in. And so the only thing that you can do is store that in the actual memory itself with your data. You see the idea? Now you might have a few registers that point maybe to the base of free memory or some other things like the first free block, sort of a header pointer for that linked list. But again, there's no other magical memory. You have to store this all in your memory itself, and it's usually with headers. So keep that in mind as we talk about these things. So when we're identifying reclaimable space, this is space that maybe is in an allocated block that can be used, but that was being used, but you realize, you know what, I can make this free. And so what you have to do is actually update the headers to make that free. That means you have to mark that block as free, you have to integrate it in with the free list, and so on. Some of these too we'll talk about, maybe I just freed up this block and this block next to it is already free. Let's do what's called coalescing the free blocks to actually make one big free block in case something big comes along to allocate later. Okay. So keep that in mind as we go through and sort of reclaim it. there is no other system that's managing that. We are. Okay? This is part of the memory management system for the language. All right, now, one other key idea is, if we're going to go through trying to find out what can be used, most of the time, the way that you begin accessing some piece of data is through a variable name. Okay. It's really the only way you can sort of start to use it, unless it's something that's in the middle of being used. Remember we talked about things like anonymous functions? I can store them, give them a name, or I can use them right away. So those are really the only ways to use any data. Either I've given it a name, or it's part of some other data structure, or I can, it's something that's sort of in flight that I'm in the middle of using. These ideas together form what's called the root set. So the root set is the named entities in the program, and then I can go out from the root set and say, okay, well, everything that's a named entity, a variable, I can access. Anything that points to, I can access. Anything that points to, I can get to. So the idea is we'll typically start with the root set and then look to see if it's reachable. So this notion of reachable from the root set is the basis of most garbage collection systems. Okay. Talk about one reference counting that you've seen before that actually doesn't look at a root set, but almost everything else does. So the idea is start at the root set. If it's reachable, then if it's reachable from the root set, we'll look at all the things that are reachable from those, and then reachable from those, and traverse outward until we get to everything that can be reached by starting at some named variable. And the assumption is if I cannot get to it that way, I cannot get to it at all, and so it's safe to throw it away. This is why automated memory management, by the way, works really well with, so let me just ask you, so Java uses pointers, right, under the hood? Can you directly manipulate a pointer yourself?
Yes.
You actually can't in Java. You just pass around objects or other data types. There is no pointer type, even though it uses pointers under the hood. And actually, by the way, it's changing those pointers on you all the time by moving stuff around and not even bothering to tell you. And we're going to talk about why it can do that later, and you don't care. However, C++ has a specific pointer type. I can take that pointer type and, by the way, cast it to a long. And then my system thinks, oh, there are no pointers to this data, so I could throw it away. Nah, I'm going to fool you. I'll pull out the long, I'll cast it back to a pointer, and I could start trying to access that memory again. Okay? First off, don't do that, right? It's just really bad programming style. But it also totally undermines anything any kind of ARM automated system's doing. So in anything doing automatic memory management, you usually won't see facilities in the language for directly manipulating and messing around with those pointers. All right. So this idea again is you'll have some root set of references in the language. Those will point into the heap. So you have things that are immediately reachable from the heap here, but then those might be reachable and then reachable and so on. Ultimately, though, you have other things that they are not reachable from the heap, and those are our targets. That's what we're going to try to throw away. So in C, C++, C# kinds of things, you're typically going to have, so you have static, global kinds of things. Those might contain pointers into the heap. Your stack might contain local variables that are pointing into the heap, and then you might have a couple of things that are in registers because they're in the middle of some computation that still might also be pointing into the heap. That is, in essence, our root set. There are things that the programmer can access by name, whether they're global or local, and then again, possibly a few things sort of in flight that are stored in registers. So this question, what's the equivalent in our interpreters? We've built an interpreter. What's the root set at any given time in the computation? the environment. The environment is our set of named entities, and then that one's parent environment and anything in the current environment chain is in scope and can be used. Now you have to be a little careful too. I can actually have things that aren't currently in scope, but I might have a function that I can call within scope, and then within the scope of that function, it can actually reference variables because of static scoping. And we've seen that kind of behavior before. So you have to consider closures as part of this reachability kind of a notion. All right, so let's get into specific algorithms. You've all seen the basic idea of reference counting, right? Have you seen that before in classes? Do they still talk about things like smart pointers in some of the C++ programming classes, or no? Okay. So the basic idea of reference counting is, let's even back off of this idea of reachability from the root set. So let's use an even weaker assumption, which, by the way, is going to give us less utility. It's still sound. All these things we'll talk about are sound. The question now is the trade-off between efficiency and utility. So first approach, actually, before we get to reference counting. One approach, and I may have mentioned this last time, I think I may have mentioned it in one of the sections. One approach is just don't garbage collect at all. There are actually a lot of things that do this. There are a lot of programs that will start up, run to completion, allocating memory, never bothering to deallocate a single bit, and then will write out its results in some fashion, terminate, and done. It never deletes or frees up memory. It's simply just, when the program terminates, all that memory gets freed up in that great delete in the sky, okay? And that's a perfectly valid way to do it. So even though back in 235 or other classes we kind of beat into you must free up your memory. No, actually, if you're planning to just run and terminate, you don't need to free all that up beforehand. The OS will actually just take the entire set of stuff that was handed to your, remember, the programming, the way it basically works is an OS gives your program a chunk of memory, and then your language is managing the heap within that. There's not one single heap that's being used by all the different programs. Every single one has its own heap. And so when a program terminates, it doesn't care anymore what's actually in its local heap. It just returns the whole chunk of memory back to the OS. And so this is a perfectly valid way to go for things that run and complete, or possibly run and, so typically things that are going to keep running, that's where you need to be careful about freeing up your memory. Now you'll notice this mentions the Apache web server uses this kind of an idea. Obviously a web server keeps running, but one of the things it will do is spawn off a new process with memory allocated to that process, which will then do its work and then just free that all up and come back. You're going to see me using some illustrations like these. Basically, greens are reads, yellow I believe are writes. You'll notice the green sort of fades from a brighter one to a paler one. And eventually you're going to get down to sort of these grayish ones, which I believe are ones that can be reclaimed. So, in other words, the idea is just keep growing and growing as more and more is allocated. Next approach. All right, So remember this idea that I just mentioned, how we're going to distinguish live objects from garbage. The key is we're going to look at, can it be reached? And if it can't be reached, it can't be used. Okay. And again, you typically design the language so that that part of it, if it can't be reached, it can't be used, is true. That there aren't backdoor workarounds with it or anything. So we're going to focus on a few main ways. One is reference counting. So the idea is we're just going to count how many things are referencing that particular object. We're going to count the pointers to a particular thing. By the way, when I say object, I'm not necessarily implying an object-oriented language. Folks that talk about memory management systems just use the term object as some generic chunk of allocated memory in the heap. It's stuff. Okay. So reference counting, you're just going to count how many pointers point to this object. And if there are no pointers to it anymore, it can't be reached. Right? And it really is just that simple. But that's a very weak assumption. We're going to talk about why it might still have pointers going to it and still not be reachable. Marking is where this idea I talked about before. We're going to start from the root set and go out and recursively try to find things that are reachable. And we're going to talk about marking approaches that actually sort of mark those. They literally will set bits in the header that just simply say, yep, I can reach this, so I can reach this one, I can reach this one. Oh, here's this stuff I can't reach. Let's go ahead and free that up. And then copying, we're going to talk about copy strategies. This one doesn't involve marking them as used. The idea is we're going to copy them over, and anything that's left is treated as reclaimable space. Okay? So we're going to use these different strategies. All right, reference counting. Reference counting, again, you start from a root. You have a root. All of these you'll have a root set. Reference counting doesn't actually even use the root set, other than these are pointers. So part of your header that you're going to store with every object will have a count of how many pointers are pointing to that object. So here's one pointer, 2 pointers, one for some of the others. Here's 2, one going this way, one cycling back. And so what you do is you inject into your code every time you assign this pointer equals that pointer, you increment the count. So if I assign a new pointer, if I create something new and assign a pointer here, I would look at this and say, oh, there was already one thing pointing to it. I'm making another pointer to it and increment that to 2. Okay. So if I changed a pointer, if I make this one change from this one to this one decrements from 2 down to 1, and then this one would now increment from 1 to 2. So you inject that code, so you either do it on the fly while you're interpreting it, or if you're compiling the code, you actually inject it into the compiled code. It's not just the user's code. Inject it in around every pointer manipulation and every pointer assignment is code that will increment and decrement old pointer, what it used to point to, and decrement what it used to point to, and increment what it now points to. So, what if in that process, so you'll notice, by the way, as this one is going, it's continuously actually freeing things up as soon as they become available, right? When do you know that you can free something up?
It has 0 references.
Yeah, when the reference count gets down to 0, you free it up, and you do it immediately. There are some systems, by the way, that will just simply say, I've detected this as 0, put this on something that can be reclaimed, and then periodically do it later. But the simplistic or most direct form of it, the most common you'll find, is free it up right away. So again, you inject code in that says, decrement the pointer it used to point to, and oh, by the way, if that's now 0, delete it, and then increment the pointer of what it now points to. Okay. And so you'll notice that things are freed up right away. This is one of the big advantages of reference counting. All right, so now let's think about some disadvantages. So let's go back to our goals. Soundness. Will this ever throw away something that a user might use in the future? Okay. It can't, unless there's some weird way of being able to assign a pointer to something where I don't, as the language, don't actually know that you did that. Like that weird pointer casting example that I mentioned in C. By the way, you can. I asked if you had seen this in C++ programming classes. A common thing that's done is you can actually build. So remember, you have a copy constructor, right? You can actually build into your assignments in your C++ classes. you can actually, even if the language isn't doing it, you can build your own stuff that does that. And so you can actually keep track of your own, these are sometimes called smart pointers. They're sort of a class of pointers that as you make copies between smart pointers, so that there's sort of objects whose purpose is to point to other objects. And as you copy between them, they'll do the appropriate incrementing and decrementing and calling of delete. And so you can actually code this yourself. A lot of languages, Swift and some other things like that, will just inject that code right into the compiled code for you. So, perfectly sound. Now think about utility. Will there be things that could be thrown away that aren't? Besides the whole undecidability. Yeah.
Yeah, I was looking at the arrows that point to the down and then back up.
Yeah.
And if you delete the one on top, they're still pointing at each other, but you can't reach them.
Exactly. If I, suppose I just delete this object, well that might delete this and might delete that as those go down to 0. Or maybe I just change this pointer to point to something else. Now, this one has a reference count of 1, this one has a reference count of 1, but there's no way to actually reach that from the root set. You have cycles that are saying, hey, I know about you, you know about me, we're here, right? Nobody, nobody's going to take us down, right? Even though nobody else in the world even knows about them or cares. And so, again, pardon the anthropomorphism, but the idea is that those cycles cling together and do not get garbage collected with reference counting. Another issue, all right, so, sorry, I'm just going to go back to this automated code analysis idea. No, sorry, I'm just going to skip over that. It was just to sort of revisit this idea of the decidability. So problems with reference counting. Again, if I take this one and I change it so it's a null pointer or pointing somewhere else, I've got a cycle floating out here. And those little islands of cycle garbage don't get collected with reference counting. So that's one of the issues. It will eventually have memory leaks that way, as long as you allow or create cycles in your data. Can you think of any other disadvantages?
Is it slow?
Yeah, well, so yes and no. So when is it doing its work?
When you reference and dereference.
Every time you reference and dereference, or anytime you actually do an assignment of pointers, okay? Which means it's in the middle of your code running. It's injected these other increment, decrement, check, and delete kinds of things right in the middle of your code. Maybe in the middle of some really speed critical section, you don't want that. Now the advantage is you don't have an explicit, separate, what's called a garbage collection phase. Most of the other systems will operate in the sense that, in fact, all the other ones we'll talk about, I'll keep allocating memory to you as you ask for it, and then when you ask for something and I don't have enough free memory to satisfy that, then I'll trigger a garbage collection phase so that hopefully I can now answer your request for more memory or for a new allocation. And this is called on-demand memory management or memory collection. By the way, many systems will actually provide an additional hook that lets you as the programmer say, hey, I'm sitting here idling, waiting for a user. Now might be a good time to go ahead and take out the trash so that it's all good and ready to go for when I actually might need you to do some stuff. Okay. Java does that, by the way. Have you ever run a Java program and had it just suddenly like stall up or stall for or pause for a moment and then runs fine and then pauses for a bit? In many cases, you'll see that if you're doing extensive memory allocation and deallocation. Then those are the garbage collection passes fitting in. Again, you can actually control and initiate those on your own within Java. There's an API for doing that. All right, so you've got these two issues really with it. One is cycles, and it turns out that's kind of unavoidable with reference counting. The second is this issue of, yes, I get the advantage of there's no explicit pause and slow down while the garbage is being collected, because it's amortizing that cost across all of your computation every time you're manipulating, you're doing pointer assignments. So those are the pros and cons of it. You'll notice then, it actually ranks fairly high in efficiency because even though it's injecting that stuff, by making a weaker assumption here of if anything points to it, I don't always have to start out from the root set and traverse out. So let's look at this issue of this sort of amortized cost over things. There is a strategy that's sometimes used called deferred reference counting. And the idea is this. So think about this actually in terms of motivation. You have a linked list of 1 million things. Now, you want to traverse through the whole thing. Let's set a pointer to the first one, right? P equals head. And then you do whatever you're going to do with that, and what do? Right? P equals head, or P equals P arrow next, right? And next, and next, and next, and next, all the way through those million things. Now think about it. Increment, when I've assigned to the first one, now decrement and then increment, and now decrement and increment, now decrement and increment, and it's doing that all the way through the entire traversal. And maybe that's sitting there in one loop, but in the end, all the counts are really just back to what they were before, because you just have some temporary pointer that's walking through the structure. So one way you can do this is to recognize that that happens a lot. Tree traversal, going through a linked list, traversing, and so on. So one way is you actually will only count references in the heap from, so you'll only count references from one heap object to another. Okay? Not from things that are actual variables in your root set, and most especially things that aren't that are on the stack. Because stuff on the stack, pointers that you're allocating in the stack, are probably just local variables for some routine, and they're going to go away. And by the way, you don't want to have to actually then sort of go through and deallocate or decrement all the counts when those go away. So if we go back to this example, here's a pointer from a heap to heap object, or we'll just call it a heap to heap pointer. This one would have a count of 1. This one is only pointed at by the root set, and so it has a count of 0, but I don't throw it away. Okay? Now it's really easy though to identify those because they're reachable immediately from the root set. So this one might have 0, this one might have 0, all the rest would still have the rest of their counts, including this cycle sitting out there being a problem. So what I can do then is I just only count those references from heap to heap, and I don't count the references from the variables. Right? Now what it means is the counts might be wrong. There might be a count, but the thing is the counts are always underestimates. So in other words, if I determine that the count really, really is 0, then I can count on that. But if the count is 0, I may have to check to see if there's some of these other pointers that I'm not counting. No pun intended. But before I actually go ahead and throw that away. Now, one of the things that you also do is you periodically scan the stack and update the counts. So in other words, let's go back to this example. Maybe in this example, I actually start with these actually being 1. Maybe I allocate some new variable and I point it to here. Well, what I would do is not increment that to 2. I just leave it 1. And then maybe that switches from here to here as I'm traversing down. Well, I don't decrement and increment, I just ignore it, because the thing that's actually the new pointer pointing to these things is something that's being allocated directly in the root set, especially something on the stack. And so periodically, though, I might go through and update the counts, because I know that I've sort of underestimated slightly, because I'm not going to count everything. But the idea is you're avoiding that amortization over all the code. So the idea is that you don't count the references from variables, or you count them when you're updating, but then as they're changing, you just don't bother incrementing, decrementing if the thing that's pointing to it is some named variable. And then periodically, again, you go through the stack, find those named variables, update your pointers accordingly. But you still have to sweep. So this is sort of a hybrid. You're saying, okay, some of these I'm not going to update, but I still will do a pass out from the root set to update these periodically. Now, sorry. Any questions about reference counting? All right, let's talk about another technique. We'll use our remaining time for this one. How many have heard of or seen or even implemented mark and sweep? Okay. I'm asking because there's a time where both of those used to be taught in some earlier classes, and so I just wanted to calibrate. Here's the idea of mark and sweep. I'm not going to count references as I go through. I'm not even going to keep a reference count. What I'm going to do is I'm going to do on-demand garbage collection. I'll just keep allocating stuff until such time as you need more memory. Or, by the way, you can also set, again, I mentioned user-initiated. Some systems will just set up a timer on it too. So periodically, it will just try to update that. And so that's what you're seeing here. It's allocating chunks, and then you'll hit a phase where it will now go through, start marking things, and freeing up what it can. Okay? So the idea is, again, we're going to do an on-demand garbage collection. And we're going to do it by starting from the root set. So in other words, literally, you ask me for memory. I determine I can't satisfy it. I'm going to go initiate a garbage collection pass. Meanwhile, your memory allocation request is still sitting there, and your the whole program is coming to a halt while I clean up the garbage. Okay. So the way that you do this garbage collection phase is you start from the root set. I'm sorry, actually, let me back up. We're going to keep, as part of our header, a mark that says you can be reached or you can't be. So when we start our garbage collection phase, the assumption is nothing can be reached. So we clear all the marks and we just say, you all can't be reached. Then we're going to start with the root set. We'll look at everything that the root set points to, and we'll mark those as reachable. And then we'll take something that was pointed to by the root set and look at what can be reached from there, and we'll mark that as reachable. Now, usually this is done in a depth-first fashion. We're just going to traverse out from the root set. Think of it as the root of a tree spreading out into memory of this object points to this object. Actually, it's really more like a graph. So the idea is we're going to actually go out and keep marking stuff, traverse as, in other words, we're going to mark what's reachable from the root, what's reachable from those, what's reachable from those, and so on and so on. Now, in the end, anything that's still left unmarked or marked as unreachable, that's fair game now to be garbage collection or garbage collected. So we'll have a separate pass through cleaning all those out. Hence, two phases. One is mark, and the other is sweep. And that's the name of it, mark and sweep. You see the core idea? So let's look, so what would happen is, I don't know if we actually, I don't think we have a slide for this. If I go back to this kind of a thing, what would happen is all of these I would mark as unreachable. Then I'll start with this one in the root set and say, okay, check, you can be reached. Do you point to anything? Now, by the way, how can it know? These are just bits in memory. How can it know if they're pointers? Yeah.
I'm just guessing you'd have to put something in the header that says this.
Yeah. You'd have to have something in the header that says what type this is. Or your program statically could be keeping track of, this is of type pointer to some object, so I know how to interpret that. The main thing is you know the type of this object, so you know which fields are pointers. And you know what those are pointers to in some, through some means. So now I can go through and I can mark this one and say, yep, you can be reached. I go back to the root set. So it's this depth first traversal. Go back to the root set. All right, that points to here, check. That points to here, check. Points to here, check. Recurse back. This one points here, here. These each get marked. And then I come back. These have all been marked. These are sitting out here, hugging onto each other with reference counting. But basically, in a market sweep system, they just never got reached. So the garbage collection pass comes through and says, all right, we're going to free up this block and this block, and we're going to add them back into the free list chain. And again, typically try to coalesce. When you have multiple adjacent free blocks, you want to try to coalesce that into one large free block. Okay. And here's why. Let's start looking at some of the issues of mark and sweep. And let's just watch the illustration for a minute. By the way, I think I